To the next edition of the TSVP talk series, and we're very, very happy to have Belen Sainz with us, who's a group leader at the International Center for Quantum Technologies in Gdańsk. It's a well-known institute in Europe. So Anna has done her PhD in Barcelona under the supervision of Antonio Assin at the Institute for Photonic Sciences, also another well-known institute in Europe for quantum information. Then she went on to Bristol for her first postdoc, then Perimeter Institute, and after Perimeter Institute, she has become, the group leader in Gdańsk. She's a foundational thinker, thinking about the foundations of quantum information science, but also foundations of quantum theory more generally. Mm-hmm. And she will now tell you why you should be interested in that talk, in that topic.
Mm-hmm.
Stage is yours.
Thank you so much. Let me see. There we go. I should have turned this on late. There we go. So thank you very much for the introduction, and thanks for the TSVP team for giving me the opportunity to come visit, and for arranging everything so smoothly, and all of the support that they give us it's really, really good. So today I want to introduce you to the very big field of quantum foundations. I don't claim that I'm going to give you a comprehensive introduction of the field, because we will need maybe a full week for that. But hopefully I can give you some snapshots that then you can, be motivated enough to go and, do a little bit more, inquire by yourselves if you're interested. So yeah, maybe then try to start. With this. There we go. So, quantum revolutions, plural, because some people argue whether it's one, two, but something that we can agree on is that in the last century, things happened. We found that suddenly the way that we thought it was okay to understand the world was no longer the case. There were experiments that were defying all of the understanding that we had so far, and basically we just had to let go of our way of thinking and try to come up with new ideas on how the world can actually be. And this was, a revolution, and it lasted for a very long time, and it's still ongoing. And somehow, the way that I try to think about this is that this revolution basically brought us with a new toy. So this revolution came and introduced this amazing new toy. We have here our beloved Ant-Man. And, you have a new toy. And different people have different ways to think about the world, or to different interests and different ways that things that they like. So, you have different children that, when prompted with a new toy, they might be thinking different things. So for example, we can have a small kid, like a toddler, and all they want to do at that age is just to chew on things when they're teething. So they see a new toy and they're like, oh, that's amazing. Can I put it in my mouth and chew on it? Mm-hmm. And you can have maybe older children that actually look at it and they're fascinated. It's like, oh my God, it moves. How is that happening? Does it have some external batteries, or this is some internal battery that are charged with a USB port? There are different things that people can start thinking about when they're giving a new toy to play in Christmas. And this somehow, even though it's a nice story, it highlights different ways that people think about, or that different thoughts that are triggered in people's minds when they are confronted with something new. So some people may wonder how something works, and how people may wonder how to use it. And these are two different ways that people, in physics in general, but in quantum foundations in particular, can think about it. And this is basically the two main kind of ways of thinking about research that stemmed when the revolutions started happening. So that's somehow where we are with the quantum revolutions here. But I want to somehow give you an example of these two different ways of approaching the problem, a bit more tailored at what we do, like maybe in the broader field of quantum information. So example on the where you're thinking how to use it. And for this, well, let's assume that you're at home and you're given a computer, and this computer is quite an old computer. We can see it here, and it's it's a bit limited. All it can do is perform linear operations on its inputs. So what does this mean? This means that you have some classical bits here, that those are the inputs that you give to your machine, and then the computer will compute some sort of function of those numbers that you gave it. And this function will only be a linear function. You can add them or multiply by a scalar, but you can't do really much with it. But you want to do something. You want to do, for example, some nonlinear computation. I want to be able to multiply those numbers that I just gave the computer. So what do I do? Is there anything that I can do? And well, something you can do is to bring in your new toy, this new toy that the quantum revolution gave you. And a particular form that this toy can have, for the sake of the example, is, well, we have two physical systems, two correlated physical systems. And what we do is now we take this computer, interacts with this new toy by taking the information that it was fed, it gives it to the toy. With these classical values here, we choose measurements to perform on these two physical systems, and then obtain some outcomes, A and B, of the measurements that we perform on these two systems. And the values of those two classical variables, A and B, is what the new toy feeds into the computer. And now the computer, with these new things, what it does, like, oh, I have these two strings, I can perform linear operations, I can add them. So, we can say, okay, computer, we're happy if you give us as an output of your computation the addition of these two numbers. Now, if one chooses or is given this toy in a very tailored manner, then, for example, if it has certain statistical properties, this specific toy, then actually one would be able to see that the way that the outcome, the measurement outcomes are related statistically actually corresponds to the product of the two measurement choices. So by just performing this linear operation here, the computer is actually giving you as an output the product of the two numbers, which is what you wanted here. So in a way, by complementing the computer with this new toy, we managed to promote its linear operations capability to a nonlinear one. So this is, what people say that, we have quantum resources and we want to use these resources to improve or enhance our capacities for performing computation or communication or whatever. So it's like this sort of spirit. And look here that actually all that we needed for the purpose of our example here was just knowing that we could give our device some values X and Y and obtain some values A and B. We didn't really care what was the inner functioning. I mean, it could be whatever physical system. Actually, this is just for simplicity, I chose this thing, but it's not really physical. So don't try to actually go and build this in the lab. But the idea is that, you don't necessarily need to go into the details of things in order to try to use the new toy that you have access to. On the other hand, there is the other kid, the slightly older kid that wants to try to see, how it functions. What can I learn about what things mean? And this kid, let's suppose that we have a slightly different situation than before. And we have two kids that went to kindergarten and they were given, these two toys, and they have this box that, they just push buttons on the top and then some lights are lit up. And, they can, press the button that is in the left or the button that is in the right, and then the box suddenly becomes, blue or red. And they're playing, in kindergarten, and then pickup time, they go back to their houses, but they want to continue playing. So they say, okay, we're going to play together even though we're not together. And what we're going to do is at certain times between the time we arrive home and the time that there's dinner time, we're going to choose a button to press, and we're going to see what light the box ends up being lit up in. And, they do this, and then they go to school the next day, and they realize that, oh my God, whenever we both choose to press the right button, then the colors of our boxes are different. But in every other case, the color of our boxes are the same. And they're like, how can this happen? Like, how can that be? Like, are the toys secretly connected and they can communicate to each other? Or did we actually do something when we were at school yesterday and they, there is something that is telling both toys what to do? Or if these two things are actually plausible, how do we go about choosing one over the other? And is there actually something very, very non-classical going on here? Or could we just have built these things by, in the garage with the things that Dad has in the cupboard? So, all of these are questions that can stem in people's mind just by observations on what this new toy does. So this kind of thinking is the thinking that is somehow that comes with the what it means, or how does it work. Now, this was somehow an introduction of, these different types of ways that people can start thinking about or working on or focusing on when prompted with like a new challenge or a new situation. But now I want to get a little bit more into things that the way that people function or people think about things in the realm of quantum foundations. So the first thing that I want to point out is that there are two different trends of like behaving and acting and doing things when you are doing research in quantum foundations. And one of them is called operationalism, and the other one is called realism. So maybe as a kind of show of hands, has any of you heard these words before? If yes, you can raise your hand. Okay, so some people might have heard about this. Let's see if they actually agree on what I'm about to say or not. You're allowed to disagree. That's a good thing about the field. But, if you have never heard of this, then you might be prompted to think, oh, realism is related to, how things work. And operationalism is related to how to use things. And, well, it's kind of a good, guess, it's a thumb rule, but it's not really quite there. So this notion, this concept of operationalism and realism pertains more to what it is that you use or what technique or reasoning you approach the questions of how to use it, how it works with. So, for example, an operationalist will say, I only rely on what I see. And they will say, okay, so what is it that I have? I'm in my lab. I know that I can, I can choose the preparations procedures. I can, I have a record of what is the name of the outcome that I obtained in my experiments. I have the statistics on all of these variables, but maybe, I don't know, I thought I had prepared a photon in an entangled state and actually there was some misalignment and it's something else. And, don't really want to rely on things I'm actually I don't really know, I'm not sure, or I just don't want to because of my personal approach to life. For whatever reason, I don't want to rely on all of those details. And this is the only thing, the only kind of information that I want to use in order to try to reason about the world or make conclusions about what the underlying nature that underpins my experiment is. Now, realists are the total opposite. They are, I need a deeper reality. I need an interpretation. I need to understand what's going on, but from a very detailed perspective. I need I need that there exists something that I can call a reality. So I want to be able to understand, explain, and talk about the things that underpin what we see. And I want to give physical meaning to mathematical objects that we use. And I want to know these mathematical objects, which may or may not correspond to actually physical things, like things that exist in the world. So it's two very different ways of approaching the world. And I want to maybe get a little bit more into these two to try to give you a bit of an idea. So maybe the first comment is that within people that take an operational approach to research, there's actually a distinction to be made that there's some people, but maybe not necessarily the majority, that actually take this from like a philosophical perspective, that there is actually, there's no reality to be understood. There's only what we see. So it's not that I'm an operationalist because I enjoy that way of operating, but I'm an operationalist because I truly, personally believe that there is nothing real out there. And there are other people that think of it as a point of a methodology. It's like, okay, it's not that I am convinced that there is no reality underpinning the world, and I'm not just saying that everything is just some randomness happening, but I do appreciate the way of thinking that this viewpoint brings in order to try to make scientific progress. And there's actually a nice quote by Lucian Hardy and Rob Speckens that says, operationalism is at least a useful exercise for freeing the mind from the baggage of preconceptions about the world. So if, you know, by taking an operationalist approach, you can like get rid of all of these different contradicting opinions that people around have, and you can focus on other things. And in a way, it provides some sort of scaffolding. So the methodology that an operationalist have is the scaffolding, where then you can build on. But it's kind of like minimalistic and only based on what you could see in an experiment and statistical data around. So throughout the talk, I'm going to tell you some stories on various different topics. I haven't actually gone and compiled these stories. There is a really nice paper put together by Lucian Hardy and Rob Speckens. And yeah, so I'm like getting lots of stories from there. For the sake of simplicity, I'm going to not include references here in my talk about these stories, but if you're interested, you can go and read this nice paper and check the references therein. So, stories about operationalism. So how is operationalism used or has been used in the past? Well, operationalism is, has been there since, the beginning of the previous century, at least in terms of quantum foundations. And it's still nowadays alive and well. And a first story about operationalist thinking is Albert Einstein. So when he started thinking about special relativity, at some point, he started to think how to synchronize clocks that were at a distance and how to do this operation. And by thinking in an operational way, then that led to the conclusion that, one needs to let go of the idea that that two things can happen absolutely simultaneously. And this kind of more physical sort of conclusion couldn't have been reached if there wasn't some sort of operationalist thinking that triggered it. And similarly, Heisenberg, in one of the first papers that kind of triggered the modern age of quantum theory, he started the paper by saying, the present paper seeks to establish the basics for theoretical quantum mechanics, founding exclusively upon relationships between quantities, which in principle are observable. So basically, the attitude that he wrote the paper with was an operationalist attitude. And then another of the many stories is this development of the landscape of probabilistic theories. So basically, probabilistic theories is a mathematical framework that provides that scaffolding for you to define physical theories. And by doing this, you can define like very different toy theories and compare them to quantum theory and start to think about, what possibilities could be out there and so on. And by just developing this framework and, sussing out the possibilities of things of, beyond quantum, is how people started understanding that some things that we think are truly quantum weirdness, like, for example, the fact that you cannot clone, is actually normal for any theory that is not classical theory. So it's not like, oh, this is a specific quantum feature. It's like, no, any non-classical explanation that you could have come up with for the world would have the same feature. So it's not a quantum thing, it's just a non-classical thing. So, if quantum breaks out at some point, this will still hold. Mm-hmm. And those kind of, physical conclusions stem from having done some operational thinking to begin with. And something happened with the projector. We're back. Okay. So, computer was telling me to stop talking about operationalist and start talking about realism now. So, stories about that. Realism was always there from the beginning, and is also still alive and well today. And both approaches have their virtues, as we are going to also see here. So, for example, back in the day, John Dalton was the one that, when thinking about atoms, contrary to other people, insisted that there, should be some reality. There should be things like going on and so on. He wanted to reject all of these statistical approaches, trying to see what atomic structure was. And all of the work that he pushed for back in the day basically triggered the development of statistical mechanics, with Brownian motion and things. So this realist thing actually had a very nice consequence. Mm-hmm. And another thing was, de Broglie also wanted to insist on describing quantum phenomena in terms of waves and have a full wave interpretation of what quantum phenomena are. And this is what eventually motivated Schrödinger to develop Schrödinger's equation, which tells about dynamics in the quantum realm. So this also insistence that there is some sort of physical reality underlying what we see also had consequences from the point of view of the theory and our understanding of physics. So these are two stories of how realism or insisting on a realism viewpoint on things actually triggered good progress in physics. So now that I've told you, different ways that we were prompted to ask and think about things because of quantum revolutions, and different ways that one can approach the study of quantum foundations, let me actually try to move on to motivations. Like, why would anyone care? Why, just, besides the personal preference or, what someone might like? Because, someone say, oh, it's really weird, I want to go and understand it. Okay, yeah, that's your personal preference. And, most of us might, like it. But why is foundations something that is objectively rather than subjectively valuable field to pursue research on? Two of the things that I want to mention today, because we can mention many, but let me just focus on two, is on the one hand, the ubiquitous quantum technologies, everything out there is quantum technologies. So, we're in the UNESCO year of quantum stuff. So quantum technologies is there. So let's talk about that. And then a question that I'm actually really keen on is, it might not end with quantum. So let me first start with this one, and then we will go to discuss that one there. So quantum technologies. I think that many people, either by doing research or, reading popular science articles or news, might have heard about, some of the quantum technologies that are out there or that people are doing research on, which, for example, pertain quantum computing, including randomness, for example, or quantum communications and cryptography, also sensing and metrology. You know, there's loads of different tasks that can actually be enhanced and performed better if we somehow bring in quantum devices into the task. And the thing is that even though this is technological development, and there's, of course, a lot of planning, designing, engineering, and so on going on in it, there's a key factor here that a better understanding of the theory, a better understanding of quantum theory, which is the theory we're endorsing for these technologies here, facilitates the identification and the development of the technologies. So if we don't have a better understanding of the non-classicality that we have access to, we might miss out on opportunities, on resources that we can use. And this is something that, you know, some people argue that the quantum in quantum information science actually relates to quantum foundations, not to, you know, quantum mechanics or quantum theory. So it's the foundational thinking that is needed in order to actually create the grounds, the solid grounds on which technologies then can be built. And let me maybe give you an example of this, you know, how foundational research actually enable technological development. And for this, let me focus on the case of cryptography, the key distribution. And I'll give you just a very broad overview of this. So the idea here, or the problem, the premise that we have, is that we have Alice and Bob. Mm-hmm. And they are not in the same place. They are distant. They are one, each of them in their houses. And Alice has a message that she wants to send to Bob, but she doesn't want anyone else to learn what this message is. So she wants to send it in a way that, if intercepted, cannot really be read by anyone else. So this is not a new problem. This is a problem that has been there for, you know, centuries and centuries. But, you know, the thing that at the end one needs in order to be able to perform this is to have a secret key. So a key that you can use in order to encode your message. And then by using the key, Bob can decrypt the message on the other side. Mm-hmm. So at the end of the day, cryptography is about how to, or, you know, broad terms speaking, is about how to generate and distribute these secret keys. So a way that is done in quantum information is to say, okay, Alice and Bob share, you know, a couple of toys like the ones that I showed you at the very beginning. And, you know, these toys, they have, you know, light buttons that they can press, and they have lights that are produced after pressing the button. And, you know, these are, you know, just bits encoding the choice of the button and bits encoding the color of the light that was observed. And at the end of the day, what here people do is they say, well, we have a lot of these devices, we have a lot of this correlated data that is being produced, and there are various different protocols or different ways to try to get all of this data, and from it, distill a key. There are tons of protocols out there which have different, you know, ranges of applicability, or, you know, places where one is better than the other. But so I'm not going to get into any of the details of that. But at the end of the day, they, you know, use many copies of the same device, and some of the data needs to be sacrificed and made public. So, you know, they can check that there's no eavesdropping, and then they can do some protocol to, you know, from that distill this. At the end of the day, you know, that's kind of like the spirit in which all of these different protocols are detailed. I'm not going to get into that. But so at the end of the day, what you need in order to perform this task of the key distribution is you need to have access to these correlated devices. And actually, if these devices are classical, you will not be able to satisfy the constraints that these different protocols demand in order for the key to actually be producible. Mm-hmm. And what people study at the end of the day is the statistical correlations, like the probability of obtaining certain outcomes from these devices when people have chosen certain inputs. And that's the object that they study. And that is the thing that is leveraged then in order to implement all of these cryptographic protocols. All right, I gave you a 30 seconds introduction to the extremely big field of cryptography, quantum cryptography. I haven't said anything about how quantum foundations fits into this, which is what I need to do. And this is linked to the next story that I want to tell you. And this started with John Bell in the 60s. So he wanted to know if there exists an interpretation of what we see in terms of hidden variables. He was saying, well, maybe for us, things look random, maybe quantum looks weird, but at the end of the day, there is an underlying reality, there is an underlying hidden variables, which are states of systems. We might, in principle, not have access to them, but maybe they exist. He kind of wanted to test this hypothesis of whether there is actually a reality there, or do we need to let go of that, or do we need to change our approach to what reality means? And in order to try to tackle that question, he actually took an operational approach to it and started thinking of experiments along this way. Started thinking about the correlations that you can measure when you see when you have different devices or different properties of the same system. And that led him to show that, well, actually, if there is a hidden reality, hidden variables out there, then that's not necessarily enough. It's actually probably not enough to explain our observations. So something else needs to happen. And the thing is that the tools and the methodology and the way of thinking that he developed to tackle this question is what many years later was, leveraged to write the first protocol on, this device-independent quantum key distribution. Protocols that are actually even robust to when the eavesdropper is the one that builds the device and gives it to the parties that are trying to communicate. So that is what triggered the kind of big ball that ended up here. And that's not, there are many examples of this kind of situation. For example, David Deutsch back in the 80s. So he was thinking of, an interpretation of quantum theory that is called Everett's many worlds interpretation, where one thinks, well, every time that something happens in the world, we don't have to think about, oh, this outcome happened, did that outcome. No, just the universe branches and everything happens just in a different branch. It's a very simplistic way of thinking about it. But, David Deutsch was concerned about what could be the information processing consequences of the world actually behaving like that. And he thinking about that is what made him, what led him to write the first paper on quantum computation. So if he hadn't been thinking of how to make sense of many worlds in the context of information processing, maybe we wouldn't have quantum computers nowadays. So that's also a place where foundations was instrumental for the trigger of some technology development. And then just to mention the last one, Wouters back in the 80s, he was thinking of principles to derive Born's rule. Born's rule is some mathematical thing in the quantum formalism that doesn't necessarily have a motivation, but it works. So people use it. And he was thinking, well, why it works, how can we make sense of it? And because of that, a lot of, this was right after his PhD thesis, a lot of things were triggered so that like a decade later, quantum teleportation was discovered. So that's another, example of, how a very philosophical sort of foundational question ended up with some applicability. I think that the thing that links everything here is that it's not instantaneous. But here, you needed at least 30 years for the development to happen. So we need to keep that in mind. So what contributes to this field? So what kind of people or what kind of research contributes to this sort of, the field of quantum foundations that contributes to quantum technologies? And well, on the one hand, we have the people that work on non-classical phenomena. So how to identify or characterize, certify or optimize the non-classical things that we observe and that we can have access to. Names, in case that you are interested, is people that work in correlations like Bell non-locality, steering experiments, contextuality phenomena, or people that just check causal networks where different parties, you have lots of people in the experiment, and how, the observations of the data that you have there may or not be underpinned by a classical explanation. Another people is the people that work on causal order. I haven't mentioned this yet. Causal order is basically, we're used to saying, oh, maybe I drink my coffee and then I walk, or no, maybe I walk and then I drink my coffee, but, I do one or the other. And here's like, well, that's not necessarily the case. There can be cases where the order in which you do is not like one after the other or just flipping a coin, but rather like things happen simultaneously, like in a quantum superposition. So that thing, can that be harnessed as a resource, and how? Then there's the people that work on other potential physical theories, that bring in scope. They bring in the research and what they discover of what could be there if quantum theory breaks, or if someone needs something beyond quantum theory. And that we can, try to understand what the scope of the power of technologies can be. And that can also shed light on what the limitations of quantum theory for actually performing these technologies are. And then there's also people working on causation and inference that feed into this sort of topic, like people thinking, well, how can we discover the underlying causal structure of an experiment? I'm going to get there later, so don't worry if you don't understand these words particularly, but that, can be fed into quantum technologies. Like I know people that have worked on this and now are working on Spotify, for example. And yeah, so that is kind of like the end of what I wanted to say about quantum technology. So maybe let me get to the other topic that I wanted to talk about, which is that things might not end with quantum. Like, how are we so certain that quantum theory is the end of the story? And the thing is that, well, it explains what we see. It has been experimentally verified with extremely high precision. So, people might just be willing to commit to quantum theory. Have a little bit of a warning though. So this is a quote from a book by Michelson that says the following. Let me read it out loud. It says, the more important fundamental laws and facts of physical science have all been discovered. And these are so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. So this is something that Michelson wrote in his book, 1903. And this was, a couple of years before photoelectric effect was observed and everything crumbled. Didn't really, impacted his career much. He still received the Nobel Prize, a few years later. So it's not like much happened. And well, to give him the benefit of the doubt, it was a very bold claim what he said, but he didn't really have any reason to believe that classical theory could be wrong at that time. We don't have the benefit of the doubt, though. We already know that quantum theory and general relativity are in conflict. We have these two physical theories. Each of them is applied or pertains to a different kind of limit in the kind of experiments or the kind of facts of the universe that they're trying to explain and model. but we know that they don't talk to each other. You can't put them together. And a big question is how to actually define a broader theory, a theory of quantum gravity that can recover each of these in the particular limit that they're being applied to nowadays. So we already know that quantum theory cannot be taken for granted. So we don't have the benefit of the doubt, as Michelson had back in the day. So it is really valuable to understand what parts of quantum theory can be changed, can be generalized, or might eventually have to be abandoned. So in this kind of more general line, what kind of people or what kind of research of people contribute to this? Well, we have people, like I mentioned before, working on other potential physical theories. And these, people have been focusing on trying to see the landscape of everything that could be there, and from a physical intuition, try to see how to recover or single out quantum theory or quantum phenomena from this broad landscape of possibilities. There's also people working on theory agnostic data interpretations to say, I have an experiment. This is the data that I have from my experiment. What conclusions can I draw if I don't want to fall into thinking there is a quantum underpinning that explains what I'm seeing? There's also people that work on how to interact with nature, or how to poke nature and see what happens. People that do experiments to corroborate or falsify hypotheses of people that are, thinking more broadly. And then from a broader perspective, there's the people working in philosophy of science, or more important, well, not more importantly, but also very importantly, people working in maths, because at the end of the day, these are only a few of the branches of maths that provide us with the framework and the language in order to be able to do all of this. So you can see that there's a lot of different people working or contributing to the development of this particular topic. And last but not least, I wanted to very, very briefly mention this field of causation, inference, and maybe also agents, which are very philosophical aspects or topics that actually have a practical implication and that I haven't really covered in the talk. So very, very briefly, causation and inference. What does this mean? Well, this is about trying to see if there is some cause-effect explanation for things or something else, and what is it actually that we can conclude from the data that we observe. So does smoking cause cancer? Well, we have smoking, we have cancer, we have statistical data of people that have or not those two things. What can we infer from it? Well, maybe smoking does cause cancer. Maybe there is some sort of common factor that prompts a person to want to smoke and also genetically develop cancer. Could be a mixture of all of that. Who knows? So this field here tells you, okay, from the statistical data, what sort of conclusion can you draw? Is it fair to say from your statistical data that smoking causes cancer, or is it actually not a fair conclusion to say because there are other options out there? So that kind of thing, like that, what sort of explanation can be underpinning your statistical data of your observed nodes is what causation and inference is talking about. Now, agents is, or people that work on things related to agents, that word there. It's basically about how to reason about facts and counterfactuals in the world. And the kind of example that underpins this is, well, we have, it's called Wigner's friend, the experiment. So there is the friend of Wigner here conducting some sort of experiment in the lab and drawing conclusions. And then there's Wigner here that is thinking about his friend that is doing an experiment. And then, well, you would think that Wigner, from observing here, would draw the same conclusions that his friend does here from just being inside the lab. But that's actually not always the case. So how can we actually safely draw conclusions and reason about the data that people think that people see, and so on. So before I end the talk, I wanted to leave with a collection of references. I can't really list everything that is out there, so maybe this is just a not comprehensive, but hopefully with references therein, it can guide you. So the first one is about this thinking of this framework of probabilistic theories and how to think of theories beyond quantum and how to try to reconstruct quantum theory from there. This is about the techniques for theory agnostic tomography, so how to reason about your experimental results if you don't want to assume that quantum theory explains your experiment. This is about more the need of dynamical causal structure, so how to think about quantum gravity. So it's a paper by Lucien Hardy who works a lot on that. Then for the more maybe popular topic, which is Bell experiments and Bell non-locality, there is a review paper about the phenomena and how this operational view has, allowed people to leverage this to do some information processing or secure communication. Then there is a paper by Ross Beckens called the toy theory, where he defines a theory that is not quantum theory, and is somehow a way for him to argue that you can have a non-classical theory that still can recover some sort of reality. You don't how not to potentially have to get rid of the notion of reality in order to define a physical theory. And there's a there's a pedagogical summary, also review paper by Hausman and co-authors about it. Then there's also a review paper on Wigner-Friends experiments and arguments. And then there's also, I forgot to include the authors here. So there's a paper by John Selby and co-authors here about the field of causation and inference, and lots of the references therein to get into that topic. So to finish, just want to highlight the fact that there is a difference between being a really good driver and understanding how cars work. You can be an amazingly good driver, but it might happen that a tire blows up in the middle of the road and you don't know what to do. So here, quantum foundations is basically the field that makes sure that if your car breaks down, that you know how to fix it so that you can continue driving to your destination. And things that people cover in quantum foundations were how to interpret the quantum formalism, how to what physical principles underpin it, how to reason about our observations, and how tackle all of this from the two valid and well and alive perspectives of realist and operationalist point of views. And well, quantum gravity is a need for quantum foundations to keep doing work, and then also a need, but some people might refer to it as a nice side effect rather than a need. But regardless of the words, the fact that quantum foundations has had a positive impact enabling quantum technologies is also a way to understand that, or to see that there is value beyond just preparing ourselves for the next revolution. So with that, thank you so much.
So yeah, thanks very much. I think for those not working in foundations, that was a very nice bird's eye view over the fields. Are there any questions? I think it's recorded, so.
Thank you.
Yeah,
thank you very much for your wonderful talk. So I have a question. You mentioned that quantum mechanics is not necessary to explain the no cloning theorem. So other non-classical theories can also explain that. So do you have an example of that?
Not from the top of my mind, but John, do you have? Yeah, and well, I mean, examples of theories or?
Yes. So what do we mean by non-classical theory?
Okay. That's also a question that people still don't agree on, what classicality means. But if we think about it in the terms of, the way physics was explained before the photoelectric effect and that sort of thing, then here, like this theory here, this toy theory, that's a theory that is not classical, and it doesn't admit cloning. So you can't, like in classical, it's fine. Like you have a piece of paper, you write a number, and then you can just grab another piece of paper and write a number, and you can clone information. It's fine. But in quantum theory, you cannot do it. And actually, classical theory is the only theory in which you can do it.
So classical theory means theory with hidden variables, or?
Yeah, you can think of it that way.
Well, I mean, this model also has hidden variables, but the feature is that what is operationally accessible is such that you can't know all the features of it at once. Like for a qubit, you can know the spin in X direction, but not in Y and Z at the same time. So, and this model reproduces this kind of complementarity.
I see.
But it's based on hidden variables.
Okay, thank you very much.
Yeah, like basically the idea here is that like in a theory, you have like kind of three aspects of the theory: the preparation of the states of your systems, the way that you can transform the state of your systems, and the way that you can measure the states of your system. And by classical, it's meant that all of these things kind of work on with hidden variables, and you can always if you have enough measurement capacity, you can always know what the state of the system is. There's no uncertainty, there's no problems. Here, even though you have hidden variables for your state preparations, you have restrictions on the type of measurements that you can perform, and because of that, you cannot actually see the information.
Any other questions?
Thank you for the talk. So I have just I want more to know your point of view on the measurement problem, and in particular, for example, the Penrose interpretations of the collapse of the wave function.
Well, my opinion is that I haven't really developed an opinion. Yeah, I haven't really devoted time to get into that. I think it's a very philosophical topic. I am not aware of how to try to go and corroborate things experimentally, though. And usually my preference is to try to, or for myself, to get engaged with foundational questions that hopefully at some point one can try to verify or falsify in the lab. So apart from very basics, I haven't really done any research on that. So I don't really have an opinion. Yeah, sorry about that.
Any other question? Yeah. Yeah.
Actually, this question might be related to Form 1 about kind of some theories that can explain some non-classical phenomena. But I'm just wondering, like, for example, for the case of Specken's toy model, they can explain some specific properties that you can observe in small particles. But I just wonder whether there is actually another alternative theory that kind of fully explains all the phenomena that can quantum theory or, for example, quantum field theory can explain.
Well, Specken's toy model is definitely not it doesn't explain everything. So for example, in Speken's toy model, you can have quantum entanglement, but you cannot explain with a toy model things like non-locality in Bell scenarios. I don't really know of any other theory that can explain everything that quantum theory
So
does.
maybe my question is, in that case, you can just exclude Speken's toy model as a right theory to explain some non-classicality. So, I'm just wondering whether there's a really strong kind of alternative to quantum theory so far. Like,
I don't know of any strong candidates. Usually the kind of theories that I've explored or that people have developed are more along the views of trying to understand what is actually classical and what is actually non-classical. So one of the take-home messages that you can get from this paper is that there's a different type of strength of non-classicality between, say, entanglement and non-local correlations. And depending on what sort of realist view of the world you want to have, then you might be able to explain one but not another. So it's more about taking all of these non-classical quantum phenomena and trying to understand whether they are equally strong or whether some of them could be explained in a more permissive classical way, so to say, or not. So that's a lot of the theories that are out there also in that sort of spirit. And also kind of like the frameworks that most people use, which is the framework of generalized probabilistic theories or process theories, is not necessarily, it's not a framework where you can define a full physical theory. It provides the scaffolding to explore the consequences of the probabilistic aspects of the theory, but it doesn't really discuss like the equations of motion and that sort of thing. Mm-hmm.
Any other question? So maybe one. So you mentioned examples where foundational thinking was triggering quantum tech evolution in terms of secure quantum key distribution and so on and so on. I guess more generally, it was, when we look at the history of quantum mechanics, it was first the theory that somehow works, and then the challenges to find a good interpretation or to provide challenges for the foundations. Now, do you have actually a good example of some developments in quantum info or quantum computing, where there was first a development of sort of technological development sides, but which conversely actually triggers problems for the foundations of quantum theory?
I have a memory of having made this argument at some point in a meeting a few years ago, but I can't really remember what the sample was. I have a feeling there might be one. No, I don't recall it from the top of my mind, but I have a feeling that there has been such a thing.
Would appear natural.
I think like Bell's theorem from the 60s, I think it gave like a proof of principle of how there are these non-classical correlations, these non-classical boxes, and these non-classical boxes are then used for cryptography. But then it's not the original Bell's box, the one that is kind of used. The thing is that at the very beginning, finding examples for this was very crafty, and there was no systematic way of doing it. And I think that it was when people realized that these things could actually have leveraged as resources for quantum technologies, that the need was created to have a systematic approach to certifying if the resource is there and so on. So all of the field of Bell inequalities, polytopes, space of probabilities, and everything that one learns from there from a foundational point of view, I think that was triggered by the necessity of people to say, we need tools, systematic tools, put on a computer, and it gives me yes or no. I think that's, I don't have any evidence to support this claim, but I have a feeling that there was a bit of that.
Okay. Any last question? Does not appear to be the case. So then let's thank Anna Belen again